Hello, this is Lecture 2b for ECE 361, Probability for Engineers. And in today's lecture, we're going to cover 4 topics. Sample problems related to homework 2. Second topic, section 1.6 from the book on counting. Third topic, section 2.1 from the book, introducing random variables. And topic 4, section 2.2 from the book, probability mass functions, in which we'll cover 4 of the most important discrete random variables: the Bernoulli, the binomial, the geometric, and the Poisson. So, before we get started, let's do a review of an important concept from last class, Bayes' rule. Bayes' rule is very simple. It says the following: given events A and B, the probability of A given B can be expressed in terms of 3 other probabilities: the probability of B given A, the probability of A, and the probability of B. To see why this must be true, multiply this equation on both sides by the probability of B, and note that by the definition of conditional probability, both the left and the right will then equal the probability of A and B. An alternate form that turns out to be very powerful, as we'll see in the subsequent examples, is the following. Suppose we're given a collection of events, subsets of the sample space, A1 through AN, that partition the sample space, omega, and an event B. What we're interested in finding is the probability of AN given B. Typically, we're not given that information directly. Rather, we're given information of the form probability of B given each of the AKs and the probability of each AK. It is in this setting that Bayes' rule becomes most powerful. For here we see we can express the desired probability of AN given B in terms of the probabilities of B given AK and the probability of AK. Note that going from this expression PB to this denominator here is simply the law of total probability, leveraging the fact that A1 through AN is a partition. We'll see how to apply this in a few slides. All right, let's start with a problem that helps us warm up with manipulation of probabilities. The problem is the following. We're going to fix events A and B in a sample space, omega. And we're given the following 3 items: P sub A, which is shorthand for the probability of A, P sub B, the probability of B, and this quantity denoted P sub O, which stands for the probability of A and B given A or B. And the question is, find an expression for the probability of A given B in terms of these 3 numbers. So what we want is an expression for probability of A given B in terms of PA, PB, and PO. Let's start by Bayes' rule. First of all, if I tell you that A and B are true, then certainly A or B is true, because A and B is a subset of A or B. So that equals 1. But I can view this as an event and this as an event, and I will apply Bayes' rule, and I will see that I get in the numerator the probability of A and B given A union B times the probability of A union B over the probability of A and B. The reason for doing this expression is that I've now managed to get the quantity of interest PO, or not the quantity of interest, but one of the things I want, PO, in the numerator. So I now have this equation that 1 equals PO times the probability of A or B over probability of A and B. Or rearranging, probability of A and B equals PO times the probability of A or B. Now recall that by a simple extension of the additive axiom of probability, the probability of A or B is always, for any A and B, the probability of A plus the probability of B minus the probability of A and B. Using our notation from the previous slide, we can write this expression in terms of the given quantities. Probability of A or B is PA plus PB minus PO times probability of A or B, where this expression came from the previous slide. But now I have an expression for the probability of A or B. I can solve that equation for probability of A or B and get the following result. So keep this in mind and our previous in mind for the next slide. So what that means is the probability of A and B, which we had earlier shown to be PO times the probability of A or B, can be written in terms of the three given quantities, PA, PB, and PO, as such. And now we're almost done. By definition of conditional probability, the probability of A given B is the ratio of the probability of A and B over probability of B. And substituting in the expression for probability of A given B, here we get the final answer. Probability of A given B expressed in terms of the three given quantities, PA, PB, and PO. The example is admittedly artificial, but the point is it's a warm-up exercise that demonstrates the value of knowing and being familiar with Bayes' rule, conditional probability, the probability of a union of two events, etc. Let's move on to the second warm-up problem, coins in a box. We have 3 coins in a box. One is a two-headed coin. The second, a fair coin. Third is a biased coin that comes up heads with some probability p. Here p is any real number between 0 and 1. The following experiment is run. I select one of the 3 coins uniformly at random from the box, and I flip that coin and look at the face on the coin. And I ask, what is the probability that the coin selected was the two-headed coin, given that the coin shows heads? So, the first step in any such problem is always to define events. Here we'll use the letters T, F, B, and H for the events of interest. T is the event we selected the two-headed coin. F, the event we selected the fair coin. B, the event we selected the biased coin. And H is the event that we selected the coin. H is the event that the selected coin shows heads. So what's given? We're told that the coin shows heads. That is, H is true. What is asked? We are asked to find the probability that the two-headed coin was the coin that was selected. In our notation, we're asked to find the probability of T given H. Let's clarify, to make sure we're on the same page, what the sample space is in this problem. Recall that I use a superscript C to denote the complement of an event. There are 6 outcomes in this sample space. TH means two-headed coin and heads. F means fair coin and heads. B means biased coin and heads. T and HC means two-headed coin and tails, because the complement of heads is tails. FHC means fair coin and tails. And BHC means biased coin and tails. Observe that some of these outcomes have probability 0. In particular, the outcome THC has probability 0. That is, the probability of tails from a two-headed coin is 0. I could just have easily have omitted this outcome from the sample space, but there's no problem in leaving it in. So why is Bayes' rule helpful here? Well, what we're asked to find is the probability of a two-headed coin given heads. But what's easier to answer are questions like, what is the probability of heads given a two-headed coin? This is representative of the typical scenario in which Bayes' rule comes to our aid. Additionally, observe that T, F, and B, the two-headed coin, the fair coin, and the biased coin, partition the sample space. We'll use that in our solution. All right, what we want is the probability of the two-headed coin given that the coin is a head. By Bayes' rule, that's the probability of a head, given that we use the two-headed coin, times the probability of the two-headed coin, all over the probability of a head. But the probability of a head can be expressed using the total law of probability as done here. That is, the probability of a head can be expressed as the sum of three products. The first product, the probability of a head given the two-headed coin, times the probability of the two-headed coin, plus probability of a head given the fair coin times the probability of the fair coin, plus probability of a head given the bias coin times the probability of the bias coin. And now you just substitute in. Note that the probability of a head given the two-headed coin is of course 1. The probability of a head given the fair coin is of course 1/2. The probability of a head given the bias coin is by definition p. The probability of the two-headed coin, the fair coin, and the bias coin being selected is equal to 1/3 because the coin was selected uniformly at random. Do your computation and clear fractions, and you're left with 2 over 3 plus 2p. To help build intuition, it's always helpful to look back at your answer and see that it makes sense. In this case, one thing you might do is consider some special cases for p. Consider, for example, when p is 0. Does it make sense what answer you get? How about when p is 1/2 or when p is 1? In these special cases, the structure of the problem should be simple enough that you can conclude that the math accords with your intuition. Another question you might ask is, it seems from our expression that the probability of the two-headed coin being selected, given that we got a head, is decreasing as a function of p. Does that make sense? Make sure you can answer that question. Problem 3. White and black balls in urns. In this setup, we suppose we have two urns. An urn is nothing more than a jar. We have an urn number 1 in which there are W1 white balls and B1 black balls. The second urn, urn 2, has W2 white balls and B2 black balls. We flip a fair coin. If the outcome of that coin flip is a head, we select a ball from urn 1. If the outcome is a tails, then we select the ball from urn 2. Now, suppose that a white ball is selected. What is the probability that the coin landed tails? Just like in the previous problem, we'll start by defining events. We'll use the notation H, T, W, and B. H is the event that the coin flip shows heads. T is the event that the coin flip shows tails. W is the event that a white ball is selected. And B is the event that a black ball is selected. What are we given? We are told that a white ball is selected. Therefore, the event W is true. We are asked to find the probability of T, that the coin flip shows tails, given this information. In our new notation, we're asked to find the probability of tails given a white ball, or T given W. Again, as in the previous problem, we're interested in a certain quantity, in this case, probability of T given W, but it's not immediate how to deduce the probability of tails given that a white ball was produced. On the other hand, given that we're told which coin face was showing, H or T, it's immediate from the given data of the problem how to conclude the probability of W given H. In particular, if heads is showing, then the probability that a white ball is selected is simply the fraction of white balls in urn 1, because we know we select from urn 1 on a head. Alternately, if the coin shows a tails, the probability of a white ball being drawn is simply the fraction of white balls in urn 2, because we know we draw from urn 2 on a tail. Again, since this data is reversed, what we're going to do is apply Bayes' rule. So Bayes' rule tells us then that the probability of tails given a white ball can be expressed in terms of the probability of a white ball given tail, the probability of a tail, the probability of a white ball given heads, and the probability of heads. And now we just substitute in the data, observing that since the coin is fair, the probability of T and the probability of H are both 1/2. clearing fractions gives us this result.